So this one is a capacitor, and it's not like your typical one, it's a spherical one. Radii R1 and R2, it says. Find an expression for the capacitance of a spherical capacitor consisting of concentric spherical shells of radius R1 and radius R2. You probably can assume it doesn't matter if this is filled with metal or not. I will fill it right now, but it honestly does not matter in the slightest in the calculation if it's filled or empty. So if these are hollow, be my guest. But if the inner one is filled, same result. But George, why is that? Well, because you're only integrating the potential, or the electric field rather, between here and here. The two surfaces that are acting like the parallel plates here. Can you see that this is like your parallel plates, but they've taken a little bit of a curvature, you know? That's all that's happened here. It's like your parallel plates, but in a broader context, yeah? Right. So the outer guy is the upper plate, and this is the lower plate. The principle still persists. You can calculate the capacitance by doing, again, charge free over voltage, change in voltage. Oh, but George, there's no charge on this thing. Well, when you calculate inductance or capacitance, they don't give you charge or current. You need current for inductance. You need charge for capacitance. They don't give you that because the capacitance doesn't care about it anyways. However, you can assume it for the purpose of the calculation here, that there exists some charge here. You can probably tell why they don't give it to you because it's going to cancel at the end. Okay, but we will give you again some Q just to be happy here about this. And there's another negative Q. It has to be on the other plate. So these charges would establish some electric field that looks like this, you know, going outwards from positive to negative. All right. I don't need to find the field everywhere in space. I just need to find it right now in this region. And I don't even need to do Gauss's law to do that, because you guys remember there's a principle that says if you're in an area and you enclose a spherically symmetric charge distribution, you know what this will go to. This will be basically equal as if all of that inner charge was collected in the middle of the inner sphere. So imagine again collapsing the middle sphere right now. Let me get rid of the details. But imagine that we are collapsing it to a single point at the center that contains all of that charge right there. Have you guys heard about this principle? Where these are equivalent pictures, the two that I drew right here? Collapsing spheres into point charges, right? If we're on the outside of a spherical charge distribution, it's like all the charge is concentrated at the center, and we're feeling
Yeah, I think you got over something similar like pre-midterm.
Okay. So I'm taking that shortcut here, or otherwise you can use Gauss's law. It's going to give you the same thing, of course, but I don't want to waste your time. So you're looking for that E field in that area. Well, the E field of a point charge, you know it from Coulomb's law. E field of a point charge is K, Q, or if you don't like K, 1 over 4 pi epsilon naught times charge divided by r squared. And the direction is outwards if you're a point charge, like this. Okay. Now, here's the thing. You want to find right now the potential difference, as you can see, between inner and outer shell. So I will take the electric field you just found, and I'm going to go ahead and calculate that. Now, Jeffrey, can probably answer me this question. Which of the two shells do you expect to have the larger potential? The inner or the outer?
Would it be the inner?
Yes. The field always points to V low. We got to remember that. That's important for our intuition. So the inner one will have the higher V. Now here's the drill again. If the inner one has the higher V, I can do the delta V. I got to keep it positive. So I will do the V at R1 minus the V at R2. That will ensure that I'm positive here. So the V at R1 minus the V at R2. And then you know how this integral opens up. We've done this especially with Neo. I've showed you this integral in our sessions. It's just negative again. The electric field dotted with dr. Jeffrey has also seen this. I don't know about Alina, but you two should be relatively familiar. Okay, so what happens here? This will be always the bottom bound. This will always be the top bound. I have the electric field. It's right there. So it's time to bring it in. So I'm going to be integrating this field from the inner surface, which starts at R2 there, all the way to the, wait a minute, inner minus outer, yes, sorry. I got confused myself, I'm good. So R2 will go at the bottom, R1 will go at the top, there's a negative there. You're dotting this with dr. And Neo, last year, I've promised you guys, like every time we did this dot product, I told you that what you're going to get back, with you guys, I used to write DL here instead of DR. It's the same thing, whether you see it as DL. Some people even write DS. But it's either going to be DL or DR in your course. If you do this dot product, I've promised that in the problems that you guys are covering in 241, just merge the R with a D here. So this is going to give you DR. In more difficult problems, this would not exactly work. You'd have some prefactors. If you had D5, for example, here, you might have a prefactor like this. But in the problems that you do, this always works. So you have to integrate that thing between R2 and R1. You can absorb the negative in the integral, so you can flip the bounds right now. Take outside the Q over 4 pi epsilon naught and switch the bounds because of that negative. You want to get rid of that negative so it's cleaner. You're integrating dr over r squared. Now that's an easy integral. R to the negative 2, if you integrate it, it's just negative r to the negative 1. So you have here q over 4 pi epsilon naught, 1 over, or negative 1 over r, evaluated between r1 and r2. Here we go. I can absorb the negative again in the bounds and eliminate it, meaning that I'm going to evaluate the r1 first. So my answer is going to say here 1 over r1 instead, minus 1 over r2, like that. And yes, you can crisscross them if you want. So we'll say r1, r2 at the top, minus r1 over 4 pi epsilon, and then the product of r1 with r2. You can see that the way I picked to do the potential difference, I'm getting a positive. Otherwise, it would have said r1 minus r2 if I didn't pay attention to that. So here's your potential difference. You already know what's going to happen next. Capacitance is right there. So I'm going to divide by the potential that I just found. The charge that I have on each of the plates is Q. So in the next step, I take that Q, but instead of dividing by this, right, I multiply by the reciprocal. It's just easier and more satisfying. And if I multiply by the reciprocal, bye-bye goes the Q, like I said. And out comes the capacitance. Game over. What do we think? Good capacitance question here to derive capacitance.
Yeah, looks okay.
All right. So this could be done with any object. You could have, instead of concentric spheres, he could have given you concentric shells. I don't know. Could have been anything, really. Okay. So he's telling you here a spherical capacitor with 1 millimeter gap between the shells has a capacitance of this much. What are the diameters of the two spheres? Okay, so I guess this would be taken as part A. B is taking this equation and finding the diameters, it says here, of the two spheres. There's a 2 millimeter gap. So they're telling you that delta R right now, which is R2 minus R1, is given to you. Like, this is a given thing. And do we know anything else? No, that's about it. So spherical capacitor with this much gap between the shells has a capacitance of 100. Okay. So over here, the only difficult thing is to get rid of these guys. But then again, I could always isolate R2. In terms of R1, it would be R1 plus delta R. And R1 would be R2 plus delta R, like that. And then I guess if you take their product, something special might happen here. So R1 times R2 would be the product of these two guys. I know delta R, but I don't know the radii. So I would have something like this. And then I guess if you opened it up, what would I get here? Let's see if I opened it up. Well, doesn't that lead you... It looks like you're going to get R1 times R2 plus R1 delta R plus R2 delta R plus delta R squared. And then if R1, R2 is equal to that, these should cancel. You get 0 here. Let me see. Can you get with delta? With the... No, you can't. Because one depends on the other. No, that's not going to work, is it? Ugh. So they don't give you any of the radii, just the diameters of the two spheres, they say. And it has a 1 millimeter gap between the shells. I have no idea what R1 or R2 are. But it depends on that.
Don't we have two equations and two unknowns?
We do, yeah.
So shouldn't we be good?
I guess you can use the capacitance, and you can... What I would do here, folks, instead of trying to do this shenanigans, I'll tell you. I would use the capacitance equation we derived and plug in this as delta R right now. This would be gone as delta R. And then one of these in terms of delta R. So maybe, let's say, I'm going to get rid of R1, and I'm going to place this here in terms, instead of R1, you know, I would write it like this. Where am I going? Well, I only have one unknown now, and it's R2. Once I get R2, because it is findable now, right? Very findable. You know, C delta R is 4 pi epsilon naught. I can also divide that out on the other side. And this opens up pretty nicely. You get R2 squared plus R2 delta R. And if you move this on the right side, this is now quadratic. So yes, you can definitely solve this here using the quadratic formula for R2. And once you get the R2 from here, okay, you can easily plug it back over here and get your R1 out. See? I'm not going to do it because that wastes time that is valuable to you, and I also am out of time anyways. But I hope you understand, right? I wrote delta R as the difference of the radii. I replaced R1 in terms of R2 and delta R, and then I just solved for R2, which was the only unknown. I have the capacitance, they give it in part B. It leads to a quadratic of this format. You solve it. Once you get R2, you can get back R1. Simple as that. Are you folks good with this?
Yes. George, have you sent me the group page for today yet?
No, Neil. I couldn't help, right? I was writing.
Oh, yeah. Does that include the square loop question?
I think so, yes, from yesterday. Yeah, everything is here. Let me close this guy.